Okay, in this problem, I've got liquid water flowing isothermally, constant temperature 20 degrees through a duct. I've got some inlet and exit diameters. Okay, at the inlet, it's going at 40 meters per second at 1 bar. And I want to figure out the mass flow rate and the velocity at the exit. So the first thing I need to recognize is that the mass flow rate at the inlet equals the mass flow rate at the exit, right? Because if it's going at steady state, conservation of mass tells me that, okay? So what I am going to do, okay, is find the mass flow rate at the inlet, because I know the velocity at the inlet, right? And the mass flow rate at the inlet, well, it's just the mass flow rate, really, remember, is AV over V, where this is the area, which I can find from the diameter, this is the velocity, which I can find from 40 meters per second, and this is the specific volume, okay? Now, this is liquid water, it tells me that, okay? So I don't have liquid to find I got to find the volume here, right? I don't have liquid volume or liquid water tables, right? I have table A5, but this is at very, very high pressures, at like 25, starting at 25 bar. I'm at 1 bar, okay? So what we do is we approximate the water as a saturated liquid at whatever temperature it is, which is 20 degrees Celsius, okay? So that volume is going to be right here, 20 degrees Celsius saturated liquid, 0.001018. Okay, so that's how we're going to approximate our volume, 0.001018. Okay, and again, that is cubic meters per kilogram. So from that, I can find my mass flow just using the area, which is for a diameter, it's going to be pi over 4 by the diameter squared. The inlet is 0.02 squared. Its velocity is 40 meters per second. And its specific volume is 0.001018, which I looked up in the table. And from that, I can find that the mass flow is 12.54 kilograms per second. And again, that's constant, meaning for steady state, the inlet and the outlet mass flow is exactly the same. Okay, so now that I have the mass flow, okay, I can go ahead and find the velocity at the exit using the same equation, but then knowing the diameter of the exit. So I'm going to use the exact same equation. I'm going to say 12.54. That's the mass flow. The area is what I'm looking for, which is pi over 4 d of the exit squared. No, I know. I'm sorry. I know the diameter of the exit. The diameter of the exit is 0.04 squared. Excuse me. The velocity of the exit is what I'm looking for. So this is the area. That's the velocity. Okay. And because the temperature doesn't change, and because I'm approximating it as a saturated liquid at the temperature, I use the exact same specific volume, which is 0.00101. Oh, I'm missing 10 in there. 08. Okay. So from that equation, I can then solve for the velocity at the exit, which is going to be 10 meters per second. Okay. And again, it's 1/4 of this because I'm doubling this, but again, that's squared. So it's basically 2 squared is a factor of 4. That's why I have the factor of 4 difference. Okay. Key things to remember are the relationship between area velocity and the mass flow, and then recognizing that for steady state, the mass flow has to remain constant through whatever it is that I'm looking at.